Hello, my name's Dr. Nick Bonne. I'm a Public Engagement and Outreach Fellow at the Institute of Cosmology and Gravitation at the University of Portsmouth in the UK. In today's presentation, I'm going to talk to you about the Tactile Universe project, which is a public engagement project where we're developing resources to help people with blindness and vision impairments engage with topics in astronomy. In particular today, what I'm going to be talking to you about is how working with people with blindness and vision impairment to develop these resources has led to some really unique experiences. I wanted to start the presentation off with a statement, and that statement is that astronomy is traditionally a really visual science, and for that reason people with visual impairments can often find it really difficult to engage with the subject. So I myself am somebody with a pretty severe vision impairment, and astronomy is something that I've always been interested in. But as a young person growing up with a vision impairment, it was always quite difficult for me to find the resources that I needed to understand the topics that I was interested in. When I finished my PhD in astronomy a few years ago, I was lucky enough to start collaborating with some of my colleagues on the Tactile Universe project. And so the Tactile Universe project is an award-winning public engagement project which we started back in 2016, and we use tactile representations of real data to make topics in current astrophysics research more accessible to people who are blind or visually impaired. The main goals of the project are to raise the aspirations of young people with vision impairments and to show them that astronomy is a subject that they can access if they really want to. We want to do this by developing shared accessible resources for learning and research, and we also want to be able to help and inspire other people to communicate their science in more accessible ways. Now, I mentioned before that astronomy is a really visual science, and so when we want to talk to the public about something like a galaxy, which is what's pictured in this image here, we usually show people beautiful images like this one. And this image has ridiculous amounts of detail. So we can see the central bulge of the galaxy in the very middle. We can see the spiral arms as they sort of wind out from that center. We can see the feathering and the dust contained within those spiral arms. And we can also see the small companion galaxy off to the side here that's sort of having all of its material stripped away by this much larger galaxy. So these images are beautiful, but there's a lot of visual information. And so for somebody who can't see these images, it becomes really difficult to convey this sense of wonder that we get from sort of looking at an image like this. We came up with a simple solution to this problem, and that was to make tactile images that people could feel instead of looking at, that would convey the same information as those beautiful pictures of galaxies. And my colleague Coleman wrote a plugin for the 3D modeling program Blender that is able to do just this. And so on the left-hand side here, I have a picture of the galaxy Messier 51. This is an actual image taken by a telescope. And on the right-hand side, I've got the resulting tactile model, and I'll explain how we make these. So Coleman's plugin for Blender takes the brightest pixel in the image, so the pixel that's closest to white, and makes that the highest tactile point in the tactile image. We then take the darkest image pixel, or the pixel that's closest to black, and we make that the lowest tactile point in our tactile model. And so this is usually going to be the background. All of the other image pixels then scale between these maximum and minimum heights, depending on how grey they are, and the result is a tactile image that's a little bit like a height map, I guess, that represents the brightness of this object. We can then 3D print the resulting model, and in theory people can use their fingertips to get exactly the same information from this that they would if they were to look at the original image. So you can feel which parts of the image are bright, which parts of the image are dim. You can feel that spiral shape. You can feel all those features that you can see in that original image of the galaxy, but using your fingertips instead of your eyes. And so I've got a picture here of the very first prototype model that we ever made. And so even though I'm somebody with a vision impairment who is of course interested in astronomy, everybody with a vision impairment is quite unique in how they've adapted, how they interpret things. And so we wanted to make sure that the models we were making were going to work for as many people as possible. And so in 2016, with some funding from the Southeast Physics Network, we were able to run a local pilot program in Portsmouth. And part of that pilot involved working with a local vision impaired support group to test these models and to basically get suggestions for improvement. So we wanted to find out things like what size the models needed to be for them to be the easiest to use, how high the tactile features needed to be for them to be easy to interpret. And so we printed a variety of models that were different sizes, had different tactile heights. And we took these to the support group and got their feedback on what worked and what didn't. And so it turned out the best parameters for these models were to make them roughly the size of a postcard, because that means that they're easy to handle with one or two hands. You can pick them up, you can put them down, you can rest them on a table. They're a little bit less unwieldy than if they were larger. They're also small enough that somebody completely blind just using their fingertips won't get lost. There won't be so much detail that they get lost in the image, basically. We also settled on a tactile height of 3 millimeters for the tactile features, because this meant that the features weren't sharp and unpleasant to feel, but they also weren't so shallow that people couldn't feel the changes in brightness and feel the bits of the image that popped out. And here I have two pictures of us working with the local vision impaired support group that helped us so much during this pilot. On the left-hand side, we're talking about the comparative sizes of objects in our solar system. We're using a peppercorn to represent the Earth, and we're using a beach ball to represent the Sun. And we're talking back and forth. We're trying to develop the right kinds of language to describe these things to these people with vision impairment. So some of them are completely blind, some of them have a little bit of vision. We wanted to settle on the kinds of descriptions that would work for everybody. And so the support group is really, really helpful here as well. On the right-hand side, we have another member of the support group feeling one of our tactile models, and she's giving us feedback on what she can pick up with her fingertips and maybe what's less obvious, but also how we can start to sort of describe what's going on in these tactile images. And we finished the pilot in early 2017 by organising a community event where we ran workshops using models of a number of different galaxies. And again, we were able to get feedback here on what kinds of language worked, which models were easy to feel, which models were maybe a little bit more difficult to interpret, and how we could supplement that with descriptions and with language. So working with these test groups was absolutely vital for us because the models we'd originally envisioned were quite simple. They didn't have many features. They were very sort of bare bones. But working with these test groups and with all of these people with vision impairments, different kinds of vision impairments, different life experiences, they were actually able to make suggestions for improvements that we never would have thought of on our own. And so these have actually made our models much more versatile and much easier to use. And I'm just going to go through really quickly some of the major improvements that we made based on suggestions from these test groups. So here I have a picture of the final 3D printed models. So these are our most recent versions, and these have all of the improvements that I'm going to talk about. On the left-hand side, I have a picture of the model's front, and on the right-hand side, I have a picture of the model's back. And I'm going to go into these two sides of the model separately. So for the model's front, and we made a number of different changes. Some of the people who were testing our models for us said that they were finding it difficult to work out how bright different parts of the model were compared to other parts. And so the solution to this was actually to put a raised edge around the edge of the models. And this raised edge is the same height as the brightest feature in the image. And so by bridging your hand across the model, you can get a sense for, I guess, how high up, how bright any part of the image is compared to that sort of maximum brightness. The other improvement that we made based on suggestions was to include a tactile nameplate. And so this helps people orientate the images, which was something that was really important to the blind and vision impaired people we were testing with. But it's also a really quick way of identifying which tactile model people are holding. If we talk about the back of the image now, so the picture I have here, so it actually has the original black and white image that we used to make the tactile model, but the image has been mirrored. And so the idea here is that by attaching this image to the back of the tactile model, people with some usable vision can look at this image and they could feel the corresponding tactile features on the other side. And so this allows people to use whatever combination of sight and touch works best for them. And again, this came from a suggestion from one of our vision impaired users. They said, hey, why are these models just tactile? Why don't you have a visual element as well? I can use my eyes a little bit. I want to be able to see as well as touch. And so this was a really important improvement that we were able to make as well. And so beyond our pilot, with funding from the University of Portsmouth and from the Science and Technology Facilities Council in the UK, we were able to start expanding the project. We decided that we wanted to work with young people with vision impairments and that we wanted to help inspire them, show them that STEM subjects, that things like physics, astronomy, mathematics were subjects that they could do if they really wanted to. And we wanted to turn our resources into something that they could use in their classrooms. And so we started working with 2 local schools that have a number of vision impaired students. One of these is a primary school, the other was a secondary school. And here on the screen, I've got 2 images. On the left-hand side is my colleague Jen. She is helping one of the high school students interpret the models. She's getting his feedback on, again, the kinds of language that we need to use to describe these images correctly. And on the right-hand side is a picture of me talking to a number of these students and sort of describing some of the physics that make galaxies the shape that they are. But again, those students are helping me develop the way that I talk about these objects. So with the help of these primary and secondary school students, we were able to develop a series of workshops for primary schools and secondary schools that sort of build up concepts. So everything starting off really small scales, building up the idea of scale and distance in our solar system, stepping up to galaxies, and then talking in more detail about galaxies. And so on the slide here, I've got 2 pictures. On the left-hand side, we're working with some primary school students and we're talking about the comparative sizes of the planets in the solar system. And again, we're using that beach ball and that peppercorn, but we can also use things like tennis balls to talk about the comparative size of Jupiter. So there are all these simple objects that are easily accessible, easy to get a hold of, that we can use to talk about the scales in our solar system. And on the right-hand side, we've got students to basically map out the solar system using tactile stickers and to get a sense of how separated all the planets are compared to each other. So to basically map out the distances between the different planets. We can then, once we sort of establish these local scales in our solar system, we can start talking about larger scales. So we can use tactile images of the night sky, of constellations like Orion, to start talking about what the night sky looks like, the fact that it's filled with other stars. We can then take another step further, start to talk about how those stars are all part of our larger galaxy, the Milky Way. And so we have another tactile image that shows the Milky Way edge on. And so we can start to talk about that. We can then get students to build a really simple model of a galaxy using a CD and some Play-Doh to get a sense of the overall shape of the Milky Way. And using this model, we can also communicate why the Milky Way is perceived as this really flat object, whereas it is really this sort of this spiral galaxy. So we've then carefully chosen 10 different galaxies that we can use to talk about what makes galaxies the way that they are, what gives them their unique shapes, what gives them their unique properties, why some galaxies are spiral, why some galaxies are elliptical in shape. And so we have these different tactile images, and we can do all kinds of things with these images with students. We can do sorting exercises where we get students to try and classify these galaxies in whichever way they want to. And we can also use these galaxies to step through how galaxies begin, how they might change over the course of their lifetimes, and how they might end up after all these changes have happened. And last but not least, we can also talk about the colors that make up different parts of different galaxies. And we can actually do this, again, in a really simple way. So when telescopes image things like galaxies, they generally use color filters that isolate particular wavelengths of light. So we'll take an image that really picks up on the blue light in a galaxy, or an image that really picks up on the red light in a galaxy. And to produce the beautiful sort of full color images that we're used to looking at, we actually stack these filtered images together to make a false color image. So it actually makes a lot of sense to use these individual filter images that emphasize the different colors in things like galaxies to talk about color. And so on the left-hand side here, I've got an image of the red light from this particular galaxy. On the right-hand side, I've got an image that focuses more on the blue light. And you can see that these images are really, really different. They emphasize different features. They emphasize different parts of this galaxy. And so we can use these different color images to get across a whole lot of extra information about these different galaxies. And I should add too, this is where some of the work that we've done with vision impaired people on the kinds of language we want to use has really been important. So talking about color for a vision impaired audience is obviously really, really difficult because color is such a visual thing. Instead, what we can do is actually take a step back. And so when we talk about colors in galaxies, normally we're talking about different temperatures of stars. So if we're looking at red light, we're talking about much colder, redder stars, usually older stars as well. When we're talking about blue light, we're talking about really young, really hot stars. So by taking a step back, making analogies, talking about the actual physics that's making these galaxies the colors that they are, we can actually communicate these ideas in a much better way. And so I wanted to finish off this talk with some lessons learnt, some tips, I guess, if this is something that you're interested in pursuing. So the first is that working with underserved communities like people with vision impairments can be really, really challenging to begin with, but ultimately it's a really, really rewarding experience. And you'll often end up discovering really, really unique, really unusual things along the way. You really shouldn't be afraid to use the expertise and the experiences of your target audience. So I hope I've gotten across just how helpful all of the people that we've worked with have been, how they've really helped us make a unique set of resources that would never have been as good as they are if we just worked on them in isolation. I think working with the vision impaired community has had so many amazing results for these models, and it's really made them much more versatile than they otherwise would have been. And also just the message that accessibility really benefits everybody. So all of the resources that we've made are obviously for sort of classroom exercises. We usually use these in classrooms that maybe have one or two vision impaired students and the rest of the students are fully sighted. What we do though is we get everybody to work with these resources together. So everybody's using these tactile resources to discover galaxies, to learn about the solar system, to do everything like that. And what we found is that the students with perfect vision have just as great an experience as the students with vision impairments. Everybody gets something out of using these resources, and really they just represent a different way of accessing these topics that we've traditionally accessed in really, really visual ways. And last of all, I should also point out that we've made all of our resources freely available online. So this includes obviously all of our 3D printable tactile images of galaxies and other things in space. We've also made the software plugin for Blender that you can use to make your own tactile images available for free. We also have all of our lesson plans and scripts, so the lesson plans basically for these workshops that I've been talking about, along with a whole lot of supporting documentation and instructions on how to 3D print, best practice for working with vision impaired audiences, how to deliver these workshops. So all of that's available if you are interested in accessing it. And so if you do want to get in touch with us, you can find us at www.tactileuniverse.org. You can send us an email at tactileuniverse@gmail.com. And you can also find us at Twitter at Tactile Universe. Thank you very much.